Welcome back to the deep dive. Today, we are strapping in for a pretty fascinating journey into the future of AI architecture. We're going to forget just stacking more and more layers. Our mission today is to really cut through the buzzwords and get into a new learning paradigm called nested learning, or NL. And this framework, it isn't just an iteration, it fundamentally challenges the very foundation of how we build deep learning models and, how we think about the limits of today's LLMs. The sources you sent over, they really paint a clear picture of the problem. We all see the amazing things LLMs can do. I mean, chemistry, vision, language, it often feels limitless. But you and I both know they hit this huge conceptual wall right after they're deployed. They're basically static. They're terrible at continual learning.
That inability to learn in the moment, that's their Achilles heel. And it's exactly what nested learning is trying to solve. If you put a neurophysiological lens on it, you could almost say that current LLMs suffer from a functional form of anterograde amnesia.
Wow. That's a powerful analogy.
Yeah.
Amnesia.
It is. I mean, think about it. The knowledge the model can access is stuck at two extremes. You have the immediate super short-term data in its context window, and then you have the incredibly deep, long past knowledge that was, frozen into its MLP layers months ago when pre-training ended. So it's always experiencing the present as if it's completely new. It can't properly consolidate that new experience into its long-term memory while it's running.
Okay, let's unpack that. Why does the human brain solve this so elegantly? What's the biological inspiration that NL is drawing on to fix this AI amnesia problem?
Right. So our efficiency in learning comes directly from a really sophisticated memory consolidation system. And it works across multiple timescales at once. We have at least two stages. First, there's the rapid online consolidation. That's the synaptic stage. It's about stabilizing memory traces almost immediately after something happens, even while you're still learning or moving around. And then you have the slower, deeper stage. Offline consolidation. This is systems consolidation. It happens later, during sleep, where the brain replays and reorganizes those initial memories, making them stronger and moving them into more permanent storage.
So the critical insight here is that our current AI models are basically just skipping that first step, the rapid online stabilization part.
Precisely. The core transformer architecture is built so that the information flowing through the context window, the immediate present, can never actually update the big, heavy, long-term weights. Once it's deployed, that door for encoding new knowledge in real time it's closed. They can recall old information brilliantly, but they can't effectively acquire new knowledge.
That sets up the mission for nested learning perfectly. So if just stacking more static layers isn't the answer, what's the new dimension?
The new dimension is time and structure. NL moves away from just defining an architecture by its linear depth. Instead, it represents a model as a system of nested, multi-level, and sometimes parallel optimization problems. And here's the key. Each of these problems has its own context flow and its own time scale. The big conceptual shift is that existing deep learning methods actually learn by the model compressing its own context flow.
I want to focus on that phrase context flow compression. That sounds a little abstract. Is the idea that the model isn't just compressing, say, text from the internet, but also the internal history of its own learning steps?
Yes, that's a great way to put it. Think of it less like data compression and more like internal experience distillation. The model is learning how to efficiently summarize its own moment-to-moment interactions and then store that summary in its parameters. And this leads us to the core definition of memory in this new context. In NNL, memory is defined simply as a neural update caused by an input. That's it. That's the mechanism. But learning is the meta process for acquiring effective and useful memory. It's about deciding what to store and how to store it.
And the NNL framework sees everything from a single weight to the whole network as a memory system, right?
Correct. Every single component, whether it's a huge neural network or a tiny part of an optimizer, is seen as an associative memory system. They all map keys to values, and they all compress their own specific context flow.
So how do you organize all these different memory systems when they're all operating at different speeds?
That's where the hierarchy comes in. It's defined by update frequency, which we can call 5-sol. This is maybe the most elegant part of NL. Components get ordered into levels based on how often they're allowed to change. The higher the level, the lower its update frequency.
Can you give me a real-world analogy for that $5 hierarchy?
Sure. Think of a big organization, like a company. You have level 1, high-frequency, daily operational stuff, the stock trader making trades every few seconds. Then you have level 2, medium-frequency things like quarterly budget meetings, and then level 3, super low frequency, like the 5-year strategic plan that might change once a decade. In an NO model, the components at level 1, the high $5, handle the fast, fleeting data like our short-term memory. And the components at level 3, low $5, they handle the foundational knowledge like our long-term memory. This structure lets the model make coherent updates across all these different timescales, just like a brain.
This is where it gets really thought-provoking. NL suggests we shouldn't just be designing the network, but the learning mechanism itself. Let's talk about deep optimizers. How does NL redefine something that seems so fixed, like an optimization algorithm?
Right, this is a major insight from the work. It turns out that a lot of our common gradient-based optimizers, like the one everyone uses, SGD with momentum, they're not single-level procedures at all. NL reveals they are actually two-level optimization processes.
Wait a second. SGD with momentum. That's the workhorse of deep learning.
Hmm.
We always just treat the momentum term as a simple velocity tracker. How is that a second level of optimization?
Because the momentum term itself, that accumulated velocity vector, drama t plus 1y, it acts as the inner-level optimization problem. It's basically a keyless associative memory module. Its whole job is to compress the history of recent gradients, that flow of error signals, into its own parameters. So the inner level stores the immediate context of the gradients, and the outer level updates the actual network weights, $2 one, based on that compressed history. It's like a very, very simple internal scratch pad.
So the momentum vector is trying to learn the best direction from this stream of gradient information. That makes sense. But if it's that simple, why did we need NL to point this out?
Because treating it as just a simple linear mechanism really limits its power. Once we see the momentum term as a memory module, we can ask, well, can we design a better memory module to do that job? And that's what led to the idea of deep optimizers. The concept behind deep momentum gradient descent, or DMGD, is pretty straightforward. Instead of using that simple linear vector for momentum, we replace it with a full-fledged neural network, usually a multi-layer perceptron, or MLP.
So we're making the scratch pad itself deep. The system that tracks the change is now a nonlinear network.
Exactly. And this massively increases the capacity of that module to capture really complex, nonlinear dynamics in the gradient flow. It can learn subtle patterns in the optimization landscape that simple momentum would just completely miss.
That sounds computationally expensive, though. If we're running a whole network inside the optimization loop, doesn't that just slow everything down?
That's a critical question, and it's definitely a trade-off. But NL also looked at improving the memory quality, not just its size, and they did that by focusing on the objective. See, standard gradient flow relies on a dot product similarity, which can be noisy. The researchers tried something else. By using an L82 regression loss for that inner objective, basically, measuring how well a key predicts a value, it results in a mechanism called a delta rule update.
Okay, stop there. Delta rule. In layman's terms, what does changing to this delta rule actually achieve?
Think of traditional momentum as trying to follow a crowd without paying attention to individuals. The delta rule update is more like a sophisticated, selective forgetting mechanism. It manages the memory better by only focusing updates on the parts of the gradient that were poorly predicted in the last step. It's less about memorizing everything and more about focusing effort where the model got it wrong. This makes the memory use much more effective and helps offset some of that extra computational cost.
So we aren't just designing smarter networks. We're designing smarter training routines that are learning how to learn the nonlinear structure of the training data. This is meta-learning applied right at the core.
That's the perfect way to summarize it, yes.
Okay, building on this idea of defining levels by update frequency, let's look at how NL changes the actual architecture of a large model. This brings us to the Continuum Memory System and the full HOPF model.
Right. The Continuum Memory System is basically the structural implementation of that multi-time scale idea we talked about. It generalizes the long-term, short-term view into a chain of MLP blocks. But the genius part is that each block is permanently tied to a different fixed update frequency.
So, if I'm getting this right, instead of all the layers updating on every single batch, they're organized like those corporate levels. Some layers update every step, some every 1,000 steps, and some maybe even less often.
Precisely. The parameters in the 10th block are updated only every, say, Siller steps. And for the higher levels, Sillars is a very large number. This design forces each block to be responsible for compressing knowledge that's relevant to its specific timescale. The slow updating parameters have to store only the most stable, generalized, long-term knowledge.
That makes the standard transformer block suddenly look very simple.
It does. A conventional transformer block is really just a special case of this system where k equals 1. It operates at one main update frequency. CMS gives you a principled way to allocate different kinds of knowledge compression across different timescales.
And what about the full architecture, HOPE?
Hope is the full realization of this NL paradigm for LLMs. It combines the Continuum Memory System with something called a self-referential learning module. This SRLM, it's based on insights from earlier models, and its job is to directly attack that amnesia problem by letting the model learn its own update algorithm.
How does that self-referential part work? Is it really choosing how to change its own weights?
It acts as a meta-learner inside the forward pass. So instead of the static projection matrices for keys, values, and queries that you see in normal attention, the SRLM dynamically changes those projections based on the immediate context. It learns to decide how attention should be structured for a specific input. This dynamic self-modification, combined with the multi-timescale memory of the CMS, allows Hope to adapt and consolidate knowledge in a way static models just can't.
That sounds incredibly powerful. So how did Hope actually perform on benchmarks, especially in those areas where current LLMs really struggle, like continual learning?
The results were very promising. Across language modeling, continual learning, and long context reasoning, it did really well. At both 760 million and 1.3 billion parameter scales, HB frequently outperformed really strong baselines like Transformer++, RetNet, and DeltaNet. Specifically, if you look at the common sense reasoning benchmarks, things like KIA-QA, HelloSwag, ARCC, these tasks measure a model's ability to apply general knowledge. And Hope showed consistently lower perplexity in language modeling and higher accuracy on these reasoning tasks.
And for our listeners, why does getting high accuracy on something like PIQA or HelloSwag matter so much?
It matters because it demonstrates effective learning over just simple lookup. These tests are designed to probe common sense reasoning, choosing the most logical outcome. When a model does well here, it suggests the architecture, in this case Hopi's dynamic projections and multi-level memory, is using its knowledge capacity much more effectively. It's better at synthesizing and applying what it knows.
So zooming back out, what does this all mean for the future of architecture design? Nested learning gives us this mathematically white box approach, linking complex deep learning back to optimization theory and, human memory.
Exactly. It completely shifts the design conversation. For a long time, the main philosophy was just horizontal scaling, make models bigger by adding more layers. NL shifts that focus to increasing a model's expressivity and adaptivity. It argues for designing systems with multiple, coherent update levels defined by timescale.
For you, the learner, the key takeaway here is that the frontier isn't just about bigger models or more data. It's about models that are designed from the ground up to be students' models that understand how to update themselves across different organized timescales. That seems like the only way to finally conquer catastrophic forgetting and get real continual learning.
And this integration of update frequency right into the definition of the architecture, combined with the ability for the learning algorithm to learn its own modification mechanism. That is the revolutionary path that NRL has mapped out.
Final provocative thought. If the brain's efficiency is defined by reusable structures and multi-timescale updates, and the nested learning framework uses update frequency to define its own levels, how long will it be until we see AI architectures that actively monitor their own rapid synaptic consolidation in real time? Maybe even mimicking the electrical signatures of human brainwaves to optimize learning second by second. That is the deep dive yet to come.